is 4.5 rational functions. And a rational function is the quotient of two polynomials. So if I had two polynomials that I gave you, that might be p of x and q of x, it would look like p over q of x, or it could be the other way around, and that would be what my new function would be. Okay, and we'll just look at some examples of different types of graphs of different rational functions. So our most basic rational function is f of x equals 1 over x. What that's going to look like is something like that. We're going to have some asymptotes. We'll go over what those really are. So basically this graph won't cross the x or the y-axis. And then we have f of x equals 1 over x squared. So this will be actually basically the same kind of shape up in the top corners. Okay, again, it's not crossing the x or the y-axis. Just some other examples of different types of shapes that we could have is we could have something that looks like this. And we won't really go into a whole lot right now because we're going to do tons of them. Maybe in a different color, I could also have something that looked like this guy in purple. Okay, you don't really have to draw all of these things because there's just a lot of things that are going to happen. We can have stuff that looks kind of like this. Okay, and right now we're going to graph f of x equals 1 over x minus 3. So this is going to be a translation of our basic graph 1 over x, and it will be translated to the right 3 units. Right, 3 units, not y-nits. Okay, so it will be 1, 2, 3 is where my vertical asymptote will be, and it will look something like that. Okay, so in order to find the domain, because we'll be looking at a lot of domains, so the domain of this, in this case, will be all real numbers, except you can write your fancy R, that's fine, except when the bottom equals 0. The bottom equals 0 at positive 3, so x cannot equal 3. So you can always take whatever is in your denominator to find the domain when it asks you to find domain. Okay, so if this one asked you to find or to write it in interval notation, it would be negative infinity to 3. 3 is not included. Union with 3 to positive infinity. Being spazzy. Then the next thing we're going to talk about is asymptotes. And I really always have to sound it out, and asymptotes is how I spell that. Okay, the first type of asymptotes that we're going to talk about are vertical. Those are fairly easy to find. We also have oblique and horizontal, but we'll talk about those in a second. So our vertical asymptotes can only happen where my denominator is equal to 0. but not necessarily. So what we're actually going to do is we're going to write all of our things factored out as much as possible. So 1 over x minus 3, what I want to do is try to simplify down my fraction. Since I can't cross out anything else, I will have a vertical asymptote, which we'll just say VA, at x equals 3. Okay, so let's do some ones that will simplify out and not be so nice. Okay, so the next example a lot of the things you'll just have to find what the actual asymptotes are. So for the next example, I will show you what the graph is, but you will not necessarily have to graph this right away as the start of the homework. And you might have x squared plus 2x minus 8. And we can't factor anything out of the top. And then out of the bottom, we can factor that down. So what multiplies to negative 8 and adds to positive 2. So that will be 4 and negative 2. So my x will have to equal negative 4, or cannot equal negative 4, or positive 2. And so when I actually go to look at my graph, I will have something that will have those vertical asymptotes. Let's just change it to a dashed line. And they will happen at negative 4. So in this case over here. And then they will also happen at 2. Okay, so that's where your asymptotes will look like. The rest of your graph, I'll just let you know, will look something like this. So there's my pen stopped working. And then the rest of the graph will look something like that. And then the next example we have is x squared minus 4x over x cubed minus x. So we have to factor these down completely. So I'll get x minus 4. Then I'll get x out front, x squared minus 1. So I need to keep factoring the bottom, and that will factor into x minus 1, x plus 1. And that is x over x times x minus 4 over all that stuff. And then I basically cross out whatever I can. So my x's cross out. So that just means that I don't have an asymptote at those. If I still had to do my domain is x cannot equal 0 because of this guy, and negative and positive 1. I don't really need my plus sign. Okay, but these, since these didn't cross out, are the only places that I have vertical asymptotes. What this is considered when they cross out is that I will get a whole whenever they cross out and simplify and divide to 1. Okay, so if I had to graph that, I go in and I plot my, whoops. Okay, so then I go plot wherever my vertical asymptotes would be, and they will only be at these two pieces, and they will be at negative 1 and positive 1. And then what I'm going to do is I'm going to go show you what the rest of the graph would look like. If you had to do this, you would just plot some points. That wasn't a very good one. This guy will also come down. And then I have a graph up here. But wherever it actually crosses this x-axis, it's going to be considered a whole. So really what you'll have like on your graph is just a big open dot. So we will find our vertical asymptotes from whatever the denominator is. And then let's talk a little bit about what our horizontal asymptotes will look like. So horizontal asymptotes. And in order to have a vertical asymptote, most of the time, or not most of the time, in this case, if we were to look at the example that we just did, if I had x squared minus 4x over x cubed minus x. If I look at this, I will have a horizontal asymptote, HA, at y equals 0. That will happen anytime the degree of the top is lower than the degree of the bottom. So it will be at y equals 0 if degree of numerator is less than denominator. It's less than the degree of the denominator. Denominator. Okay, there will be no horizontal asymptote if degree of numerator is greater than the degree of the denominator. So no horizontal asymptote if degree of numerator is greater than degree of denominator. And if they have the same degree, if I'll just write top and bottom, have the same degree, so these are my three things, it will be the ratio of those coefficients. So I'll show you what that means in a second. It will be y equals a over b. This is where my horizontal asymptote will be. And a and b are the biggest degrees coefficients. So an example real fast is the one that they give you is negative 7x to the fourth minus 10x squared plus 1. Then I have 11x to the fourth plus x minus 2. And what's actually going to happen is these two numbers, it absolutely does not matter about anything else over here to figure out what my horizontal asymptote is. So my horizontal asymptote would happen at y equals negative 7 over 11, whatever these coefficients are of my degree. Okay, so just remember same, bigger than, and less than. And then we have what is called an oblique asymptote. Forgot my y. And this is actually going to be what happens when we have the degree of the top being bigger than the degree of the bottom. So for example, if I had this guy, what I have to do is actually do my synthetic division, long division, whatever you want. You can pick whatever you want to do now. So I take the bottom equal to 0. I'm going to use my synthetic division because I like that a lot more. Okay, so whatever you do, I want to do synthetic division. I have to decide when my bottom will equal 0. So that will mean x has to equal positive 2 is what will go up in my corner. And I will write my coefficients down. So I have 2, negative 3, and negative 1. Since 1 is my constant, I basically make my little remainder box. And I will have 2. 2 times 2 is 4. 4 and negative 3 is positive 1. 1 times 2 is 2. negative 1 and 2 is positive 1, and really this whole piece over here does not matter. What matters is this thing right here. So this would represent 2x plus 1 since they're both positive, and this is where my oblique asymptote will happen. So then I would have to go through and I actually have to graph this line on there. So let's draw the axes. And then I'm actually going to go through and I'm going to graph 2x plus 1. So plus 1 would be right there. Oops, it's kind of hard in the same color. And then I'm going to go up 2 over 1, down 2 over 1, and I'm going to make this graph. That is where my oblique asymptote is going to happen at. This is the line 2x plus 1. And then the other piece that I have to do is when I figure out where my bottom piece equals 0, I'm also going to have a vertical asymptote at x equals 2. So x equals 2 is this line right here. So I'm going to have some graph in here, and what it's actually going to look like is going to be these like kind of crossways V's. And just a real quick note that you need to make sure you realize is that with a horizontal and oblique asymptotes, so horizontal and oblique asymptotes, the function can cross. Function can cross those asymptotes. With a vertical asymptote, the function can never cross it. It cannot cross it. So this is the vertical ones. You'll never have anything cross it, but these ones, they can kind of skip around on it. And what happens is they just really will finally even out to that piece, even if it's going up and down around. I've already put holes into one of the graphs, but we will actually talk about what those will look like. So they have the function, the function, x minus 2, and I'll just go ahead and write it factored for you. So they have x plus 1 on the bottom times x minus 2. Okay, so real quick, so even though this is factored, my domain is x cannot equal negative 1 or positive 2. These can cross out, however, so I will have a vertical asymptote, which we've already talked about, at that negative 1. But since these ones crossed out, all I get is a hole. So I have a hole at positive 2. So on a graph, your vertical asymptote at negative 1. And so all you have to do is really like label your asymptotes for me. If you guys have some graph paper, that'd be great. If not, just try to label things. And a hole at 2. So I need to then figure out where my y-intercept will be, just to have some quick graphs. So my y-intercept will happen at x equals 0. So if I plug x equals 0 into this, I will get 1. If I can do it no matter how you want me to do it. I can do 0 minus 2 over x minus 1, x plus 1. 0 plus 1 and 0 minus 2. So that will be negative 2. Then I will have 1 times negative 2. So that will all equal back to positive 1. So it will cross here at positive 1 so that I can kind of sketch my graph real fast. But then I have a hole at 2. So I'm going to make just this kind of graph. I also can just do it from my factored form of my original function. So if x minus 2 goes into both the top and the bottom, I have a 1 on top and 1 on the bottom, and I'll just be left with 1 over x plus 1. This is going to be my y-intercept. If this hadn't crossed out, it would just be your constant form, whatever your constant is. Okay, and I'll basically have the same thing over here on this side. And my horizontal asymptote was at y equals 0 because my top degree is bigger than my bottom because I have two x's here that are multiplied. Even if I were to have this in the simplest form as 1 over x plus 2, I still have to do this piece as my domain no matter what. I want you guys to do the graph matching on page 356, just all of them. And then page 357. I want you to do 3 through 33 by 3s. That's not. And 80, or oops, sorry, 79 through 98. All of them.